Okay, now let's look at the code construction. You will see that we don't use new tools. All ideas we used here for proving the theorem we used before in the previous theorems or proofs of the theorems. So look at the code construction. Again, we use an auxiliary random variables and an auxiliary channel from x to u. And then we generate again 2 to the n r plus r prime code words un of w and v. This means we also use binning again. So w goes from 1 to 2 to the nr, and v goes from 1 to 2 to the n r prime. So in totally, we are choosing n times 2 to the n r plus r prime symbols in the codebook. And again, we choose them independently at random according to PU. Now, the encoder will do the following. He get W and he get S to the N. And now he try to find a V tilde such that UN, W, V tilde, and SN is typical concerning U and S. So W chooses the bin with code word UNW1, UNWY2 until UNW2 to the NR prime. And the interference select this UNW V tilde from this bin. So if one finds such V tilde, we choose V equal V tilde and transmit XN equal Fn of UN, W and V and Sn from the codebook. If we don't find such V tilde, we transmit Xn equal Fn of UN, W1 and Sn. Now the decoder receives Yn. And now he tried to find a pair W tilde and V tilde such that UN of W tilde, V tilde, and Yn are typical concerning U and Y. If there is one or more such pairs, then choose one and put out the corresponding W tilde as W hat. If there's no such pair, then we put out as W hat just one. That's the idea of the coding construction. And you see, no new tools, always the same idea. The idea is use binning, use random coding, and use the auxiliary variable. Also for the analysis, we can use some thoughts we used already. So we are, again, I think you can check by your own that all cases cover the whole probability rule. So we use some kind of union bound. So first we start with this case that state sequence is not typical. And this probability event goes to 0 with n, we know. Then we look at the event that the state sequence is typical, but the encoder cannot find a V such that UN of W and V and Sn is jointly typical concerning U and S. And this is the same in principle that we studied for the rate distortion problem. We know that the probability of this event is small if n is large and r prime is greater than the mutual information between U and S. Then the third case. The third case, we assume that UN and Sn is jointly typical. Therefore, we know UN, Sn, and Xn are jointly typical concerning US and X. And we suppose that UN of W and V and Yn is not typical concerning U and Y. That means Yi was chosen using, we know that Yi was chosen using the probability of y conditional on s and x for all I, and we know that u, s, x, and y forms a Markov chain, and we have that yn, sn, xn, and un is not jointly typical. And then we can use the Markov lemma, which you have 2 lectures before. And we know that this probability goes to 0 if n goes to infinity. So the last case is that yn is typical concerning y, and the decoder finds a w tilde and a v tilde, but w tilde is not equal to w. And un of w tilde and v tilde and yn is jointly typical concerning u and y. So if you look at the probability of this event, then we know we have to look at all code words outside the bin. So in one bin there are 2 to the n r prime code words. In total we have 2 to the n r code words. So we have 2 to the n r minus 1 times 2 to the n r prime code words outside this bin. And that this event then happens, we know by our lemma that this probability is 2 to the minus n times the mutual information between u and y. And so we know if epsilon is small and n is large, that then r plus r prime must be smaller than the mutual information of u and y. Now we have all cases. And we can combining it, and we get what we want. We get the capacity region. First we get only the direct part, we get a rate which we can achieve. So we know we can send messages over the channel with this rate Rg, which is the maximum over all channels from S to U, these auxiliary channels, and all functions, such that the mutual information between U and Y minus the mutual information between U and S is maximized, where U, S, X, and Y forms the Markov chain. And Rg is called the capacity of the Gelfand-Pinsker problem. Of course, we still have to show that the converse holds. And again, we can show that it is enough to choose U lesser equal X times S plus 1.